Okay, so let's proceed with our next topic on multiplexers and decoders. So first we're going to look at the multiplexer. There are several different kinds or different sizes of multiplexers, and the first one we're going to look at is the simplest one, which is the 2-to-1 mux. Okay, the mux here also known as the multiplexer. So what is the function and how does the multiplexer works? So given the truth table here, so here is the truth table of the 2-to-1 mux, okay, also known as 2x1, 2-to-1, or 2-1. They all mean the same thing, 2-to-1 mux. So a 2-to-1 mux, basically what happened is we can look at the simplified truth table down here, where if s equals to 0, then y is equals to I0. If s equals to 1, y is going to be equals to I1. So for example here, we have 0, 1 here, and here is the output. So if s is equals to 0, then whatever is on I0, if it's a 1, then y equals to 1. If I0 equals to 0, y will be equals to 0. Similarly, if in the case that s is equals to 1, in the case that s is equals to 1, so here is a 0, 1 selector, then y is going to take the value of I1 if it's a 1 or 0. So here we can see the truth table that our s here, that our output y actually takes in based on the value of s. So for example here, if s is equals to 0, we know that y will be equals to I0. So that's why that you see here that y is actually following I0, so y equals to 0. Okay, y equals to 0 when s is equals to 0, y equals to 1 when I0 equals to 1. So similarly down here, where we see that when s is equals to 1, okay, when our selector is equals to 1, our y output actually follows the I1 input. Okay, so for example here, if you take one example in this one, we see that the selector is equals to 1, I1 equals to 1, therefore our y equals to 1. Okay, so here is the schematic on the block diagram, the gate level schematic of the 2-to-1 mux, whereby you have the S here connects to the inverter, connects to an AND OR logic. So for example here, if we have S equals to 0, we know that y is going to be equals to I0. So let's see how it works. So if we put 0 here, this one is going to be 1, and here is going to be I0. So I0 and 1 will give you I0. I0 plus whatever in here, we are going to get I0. Okay, and similarly, if we replace with the 1, so if we replace with the 1, if s equals to 1, we are going to expect that y equals to I1, and here is going to be 0. Okay, so here is going to be 0, here is I0. I0 and 0 is actually 0. I1 and 1 is going to be I1. I1 plus 0 or 0 will be equals to I1. So basically we can say that the output y is in fact, we can derive the Boolean equation for the output y here in the simplest case, where the Boolean equation y is simply going to be equals to, here is I0, S bar, here is I1 and S. So here is just going to be I0 S bar plus I1 S. So here is your Boolean equation for a 2-input multiplexer. So let's see, we can extend a little bit more to obtain a 4-to-1 mux. So the functionality is still the same. Let's look at the top level block diagram here first, where if we apply 0, 0, it's going to take this one. This is 1, 2, and 3. So if you apply 0, 0, I1 is going to go through. If we apply 1, 0, if we apply 1, 0, so 0, 1, 2, and 3. So 1, 0 is a 2 in binary. So what happened is the I2 is going to be transferred to the Y output. Okay. And here is the truth table, so we can see here that if we supply 0, 0, y is I0. If we supply 0, 1, y is I1, 1, 0, I2, and 1, 1 is I3. Okay, for 1, 1. And can we derive the Boolean equation? The Boolean equation. So how to derive the Boolean equation? So here is the block diagram, okay, the gate level schematic, and we can see here that here is going to be S1 bar, and here is going to be S0 bar. So you can see that S1 bar, S0 bar, here is I0, and if we supply 0, 0 here, then we are going to get a 1, 1 here. Okay, so 1, 1 there will give you I0. So I0, naturally all the others will be 0. So all this will be 0, and therefore our y is equal to I0 at the condition when our S1 and S0 are both equal to 0. So the Boolean equation is therefore y is equal to I0 S1 bar S0 bar plus I1 at the condition of 0, 1, which is 0, 1, plus I2, 1, 0 is S1, S0 bar, it's a 1, 0, plus I3, S1, and S0. So again, we can see that what happens when we give 1, 1, when we give 1, 1 here. Okay, so in the case that we give a 1, 1, in the case that we give a 1, 1, we are expecting our y is equals to I3. Okay, so in the case of 1, 1, we are expecting that our y equals to I3, and we can see here that if it's a 1, 1, this one will be 0, this one also will be 0, this one will be 0, so y is actually equal to I3, S1 is 0, which is equals to I3. Let's move on to the larger multiplexer. So we can also have 8-to-1 multiplexer. So one thing to note here is how many selectors, control selector. So here is called the control selector. Okay, mux control selector. So how many bits is our mux control selector for an 8-to-1 mux, for a 4-to-1 mux, and also for a 2-to-1 mux? So we saw in the previous 4-to-1 mux we have a 2-bit mux control selector. For 8-to-1 we have 3 bits, because at the condition when our control is 0, 0, 0, we are going to take this one. 0, 0, 1, 0, 0, 1, we are going to take this one, and so on until the last one. So in the case that we take I7 is when our mux control vector selector is actually 1, 1, 1. Okay, so we have a 3-bit control there, and similar function to the 4-to-1 and the 2-to-1 mux is when we supply 0, 0, 0, our y will take I0. Okay, at the condition that we apply 0, 0, 0. Okay, so similarly at the condition when we apply 0, 0, 1, okay, we apply 0, 0, 1, then our y is going to be equals to I1, and so on until the rest. So one thing to note here is that we can also derive Boolean equation. Okay, similarly on how we derive in the 2-to-1 and 4-to-1 mux, but this is going to be quite long to derive the Boolean equation. And the second remark is how many control selector, how many bits of control selector we have. If we have, for example, a 16-to-1 mux, how does it look like? And we can also have a 32-to-1 mux. And how does it look like, and how many mux control selector we can have. So in the case of 32/1, we have 5-bit control selector. Okay, so means that we have the S3, S2, S1, S4, S3, S2, S1, and S0. 5-bit for a 32/1 multiplexer. Okay, so let's look at some applications of the multiplexer. So the first application is our waveform selector. So in this case, we have several waveforms. They are being generated, maybe from external sources, and you are required to take or choose at one time only one frequency. So let's say at time 0, I want my signal F for 1 kilohertz, okay, and then at times 1 millisecond, for example, I would like 125 hertz. Okay, so depending on the time, at this particular moment I want this speed, this particular moment I want a different speed. So we can then use a 4:1 mux. So this is a 4:1 mux, okay, whereby we just supply, for example, if I need a 1 kilohertz, I'm going to supply 0, 0, and therefore our Y is going to be a 1 kilohertz signal. Okay, this is it, we apply at time 0, and then at time 1 millisecond, we are going to apply a different signal. We're going to apply, let's say, 1, 1. Okay, so this is at t equals to 0, and then here is at t equals to 1. We are going to apply 1, 1. So 1, 1 is going to take the 125 hertz signal. Okay, so it's a slower signal. Okay, 125 hertz. So essentially what the multiplexer does is it can select a particular input and send it to the output. Okay, so another example of the multiplexer, and here is a 2:1 mux. Here is a 2:1 mux, is to do a bus selector. Okay, to do a bus selector. So in the bus selector, what we have is basically these are 4 bits now. So these are a standard 2:1 mux. Okay, here is a 1-bit 2:1 mux. So inside here you have the normal circuit. Okay, the normal and/or circuit, okay, for Y0 and so on. And then for each bit, so this is the MSB, okay, and this is your LSB, okay. So for example, at one particular time, I want to have the value A at the Y, okay. So let's say at time 0, I want Y equals to A. And then at time 1, I want Y equals to B. So what I can do is I can just give the value 0 here. Okay, so if I give the value 0 on my selector, I am going to get here A0, A1, A2, and A3. Okay, and similarly, if I apply a 1 here instead of a 0, I'm going to get B0, B1, B2, B3. Okay, so we can see here that if I apply 0, I'm transferring these values to my output Y. Okay, so essentially it's a kind of a selector. So other applications of the multiplexer is the rapid implementation of logic functions. So for example here, this is important in programmable logic. Okay, in programmable logic they use this concept, programmable logic. So we're not going to go through in detail in this course, but later on in your senior year you will see some concepts on programmable logic. So the programmable logic concept is that we can quickly implement a function by just putting a constant. Okay, so here is a constant VDD, okay, VDD, which is voltage supply. This is ground. So we can supply a VDD or we can supply a ground value to the input of the multiplexer, and straight away we are going to get our F function. So let's have a look at how this works. So what is the min term of 056? The min term of 056 is basically saying that so in this condition we say that F is actually equals to 1 when A, B, C equals to 0, 0, 0. Okay. And the second one here, F is equals to 1, okay, when A, B, C is 5, which is 1, 0, 1. Okay, and here is also F equals to 1 when A, B, C is equals to 1, 1, 0, which is a 6. So essentially what's going to happen is when our ABC, okay, so notice that our ABC we put here as our input. So when our ABC is 0, 0, 0, okay, at this moment we want our F to be equals to 1, and therefore our F will take this value which is equals to 1. Okay, so F equals to 1 when our ABC is 0, 0, 0. Similarly, when our ABC is 101 110. We also want f equals to 1, so here we are going to put a 1 there, okay, on the 5. So when 101 110, okay, ABC, okay, f is equals to 1. So exactly here, so when we give the 101, we are going to take this and transfer the value of 1. Other than that, besides these three conditions, we have f equals to 0 according to our midterm, and therefore we supply a ground or a 0 value on all the other inputs. Okay, so let's look at another example here of what we can do with the 8 to 1 mark. So here is a 8 to 1 marks. So we can see here that we can actually put our ABC here, okay, and then the D here as our input, okay, D and D bar as our input, as well as having the 0 and 1. So what happened here is, if we have 4 inputs A, B, C, and D, okay, and we want to given this, okay, given the truth table here, okay, implement with the 8 to 1 marks, okay. So what we can do is we can actually divide this, and we can see here that our D, okay, we can see here that when our ABC is 0, okay, so when our ABCs are all 0, 0, 0, 0, we want our F to be equals to 0. Okay, that's our output F. Therefore, we can say that F equals to 0 when ABC is 0. So that's why we give the value of 0 here. So F is equals to 0 when we select 0, 0, 0 in these two conditions. What about in the second one? So we see here that when we give 0, 0, 1, when we give 0, 0, 1, okay, we can see that we want our F equals to 1, so therefore we put a 1 there. So regardless of the value of D, our F will be equals to 1. Let's look at the next one. So 0, 1, 0. So at 0, 1, 0, we know that we're going to transfer this one. And we see that at 0, 1, 0, the F is equals to 0, 1, which is in fact equals to the value of D, and that is why we put the D there. Okay, and similarly down here we can see that at 0, 1, 1, okay, we're going to put a D bar. Okay, see here. So we are actually going to put a D bar on I3 because our F is in fact is the inverse of the D. Okay, and we go through here and we see that in fact this is the 8 to 1 marks, okay, implementation of this truth table. Okay, so here is the 8 to 1 marks implementation of the truth table. We can also use a K-map to obtain the output F, okay, and we obtain some logic gates, but we can also just use a multiplexer to obtain the logic equation. Okay, let's carry on here with the 4 to 1 marks using 2 to 1 markers. Okay, so we can also break down our multiplexer into several small marks. So for example, here I'm putting my S1 here, S0 there. So at the case when all of them are 0, so if I put 0, 0, 0, S1, 0, and also S0, 0, what should be my output in the truth table? Should be 1. So here is actually 0, 1, 0, 1, 0, 1. So at the case of all zeros, then I'm going to transfer this value to the outside, which is the value of 1. Okay, should be the same then. So let's look at another example here. At the case of 1, 1, 0, at the case of 1, 1, 0. So at the case of 1, 1, at the case of 1, 1, we are expecting a 0 on the output. So are we really getting 0? So 1, 1 is 0, 1, 0, 1, 0, 1. So 1, 1 is actually taking this one. Okay, and we see that is taking a 0, and it should match. Okay, so that's the 2 to 1 marks implementation, and we can also extend to a 4 to 1 and the 2 to 1 for a 3 input, whereby we can see here that S2, S1, S0 we put as a selector. for a basic 8 to 1, but if we only have available 4 to 1 and 2 to 1, so we can put S2 there, and I'm going to put S1, S0 there. So in the case that I have 0, 0, 0, so same here, if I put 0, 0, 0 there, I'm expecting that I0 is going to go out. So here also, if I put 0 here, 0 is going to take my I0. Okay, so if I take 4, for example, so 4 is 1, 0, 0. So 1, 0, 0 is here, 1, 0, 0. So it's going to take I4 in there. Okay, let's look at the, okay, I think we are finished with the multiplexer. Let's look at the next part. The next part here is a demultiplexer. So a demultiplexer is the inverse of the function of the multiplexer. Basically what happened is when you supply 0, 0 on the input, we are going to send our input to Y0. If we give a 0, 1, then we are going to send to number 1. Okay, so similarly here, if I give 0, 1, 1, which is a 3, I'm going to send this to number 3, to here. Okay, I'm going to send this to number 3. Okay, so let's look at the internal part. Okay, so here is actually a 1 to 4 Demarks. Okay, a 1 to 4 demultiplexer. So what happened when our input is both 0? So we know that if it both 0, then we're going to want to transfer this to the outside. And what happened to the others? Okay, so what happened to the others? Okay, so we can analyze this. Okay, we can analyze this and see that actually if the condition that the condition 0, 0, okay, if the condition is 0, 0, we can see that here is going to be 1, 1, so 1, 1 here. Okay, and then here is going to be I bar. Okay, I bar, and here is going to take O equals to I. Okay, at the condition when S0 and S1 are both 0. The others are simply going to be a 1, in fact. Okay, so there might be some error here in the, okay, we can analyze the circuit here. So in the circuit here, we can see that this one is going to be a 1. So this is a NAND, so 0, 1, so this is going to be a 1, a 1, a 1. Okay, here is I. Okay, so depending on the circuit, okay, depending on the circuit, we can see that for 0, 0, I0 will be equals to I, O0 will be equals to I, and the others will be equals to 1. Okay, so let's have a look at the application of the Demarks. So in the Demarks, what happened is normally we have a shared transmission line, and here is our source. Okay, here is our destination, and we have a selector here. So let's say I'm going to have my selector here is 0, 1. Okay, 0, 1 is I'm going to take my B input to the line, and I'm going to transmit this, and here is also going to be 0, 1, and I'm going to put into the B destination. Okay, so using the same selector, here is your Demarks, and here is your mark selector. Okay, let's proceed with the binary decoder. So a decoder is different than the multiplexer. So the decoder has n inputs and 2 to the power n outputs. So for example, we can have a 2 to 4 decoder. Okay, 2 to 4 decoder. We can have a 3 to 8 decoder. Okay, we can have a 4 to 16 decoder, and so on. Okay, so let's see how the decoder works, and we're looking at the simplest one, which is a 2 to 4 decoder. So how does the 2 to 4 decoder works? So here is the truth table. Okay, TT, here's the truth table. So we can clearly see from here that if we supply a 0, 0, then we are going to get 1, 0, 0, 0 according to the truth table. Okay, if we supply a 0, 1, which is this one, okay, we are going to get 0, 1, 0, 0. So what happened here is when we give 0, we are expecting y0 equals to 1. When we give 0, 1, we are expecting y1 equals to 1. When we give 1, 0, it's number 2, and y3 is 3. Okay, so then we can also derive what is the Boolean equation. Okay, Boolean equation at each output y0. So y0 here, you can see that in fact is simply going to be a bar, b bar. Y1 is going to be this one. Okay, y1 is just going to be a bar b. Y2 is going to be a b bar, and then y3 equals to ab. Okay, so these are the Boolean equations for a 2 to 4 decoder as given here. Okay, so if you have the Boolean equation, so y0 is a bar b bar, so you have the a bar here, b bar here, so just an AND gate here, so a bar dot b bar, and here is the gate level schematic of the decoder. So a decoder, we can actually implement also any logic function, SOP functions, using a 2 to 4 decoder or a 3 to 8 decoder. So for this example, we have two inputs, so we are going to use a 2 to 4 decoder. So so in this case, we have AB equals to 1 when is 2 and 3. Okay, so our output F is equals to 1 when our input is 1, 0 and also 1, 1. And here we can actually implement the decoder like so. So let's see, we have AB, Y0, Y1, Y2, Y3. Okay, you can see we put AB here. And we know that Y0 is A bar, B bar. Okay, and we know that for this particular function is F using the canonical SOP, we have A B bar plus AB, okay, which is based on this. And here we can see that A B bar is actually from here, and then AB is actually from here, so we can just simply put the OR gate and make it equals to F. And here we have the truth table implementation using a decoder and also some basic gates. Okay, let's look at the next example here on a practical BCD to 7 segment decoder. This is the anode type. There's also the cathode type. So the anode type is giving values here. So for example, A, B, C, D, E, F, and G. So for example, if our input, okay, here is our input. So if our input is 0, 0, 0, 0, then this is light off. Okay, the anode type logic 1 is light off. Okay, light off. And here is light on. So you can see here that our G here is a light off. So here is off. Okay, so if you can imagine that this is on, and on, and this is off. So we can see that it's actually a value of 0. Okay, so it's actually displaying a 0, okay, on the 7 segment LED. So again, for example, if you want to display a 4, a 4 will in fact, let's do a 3. So a 3 will light 1, 2, 3, 4, and 5. So is something like this. Is a 3. Okay, so here we're going to supply a logic 1, okay, on A, B, C, E, F, and G. So we're going to supply a logic 1 on F and E. So we can see the 3 here. So you can see a logic 1 on the F and E, okay, for the input 3, okay, and all others is 0. So from this, we can also derive the logic gates. Okay, can you implement each of the output using logic gates? So we can put a K-map, for example. We can put into K-map. How many K-maps we're going to have? We're going to have 7 K-maps. Okay, 7 K-maps for each one of these. And for each one, for example, here the simplest one will be for C. You can see that actually our output F, okay, for C, okay, so output C is in fact is A bar, B bar, C, D bar. Okay, according to this. Okay, so then we can derive our Boolean equation. So let's look at the 823 encoder now. Okay, so we are finished with the decoder. So 823 encoder. So in the 823 encoder, this is our truth table. Okay, so this is our truth table. So we can see that here, when we give this input, we are going to get this output. Okay, here is our input, and here is our output. Okay, so it means that if I supply 1 0 0 0 0 0 0 0, I'm going to get 0 0 0 because I'm giving a 1 on I0. So I'm giving a 1 on I0, I'm going to get 0. So this is actually encoder, also known as a compressor circuit. Okay, a compressor method. Okay, it's actually compressed from 8 input and generates 3 input. So it's actually compressing the number of inputs. So here is 8 input to 3 input, and it's compressing it. Okay, so similarly you can see another example here whereby if we give this one, okay, I5 equals to 1, so I5 is equals to 1, okay, all the rest are 0, and here we are going to get 1 0 1. Okay, we are going to get a 5 because we supply a 1 on the 5. So the question naturally is, what happens if we supply something strange? Let's say, for example, if I give 1 1 0 0 0 0 0 0, and it's not in the truth table, so I put 1 both in I0 and I1, then what should be the output? So in general, the output is going to follow the smallest one, okay, which is I0, so it's going to give the output 0 0 0, and this is ambiguous. Okay, it's ambiguous, so this is overcome by priority encoder, which is the last part here, which is a priority encoder, whereby now if we supply 1 1, okay, so for example I'm going to give 1 1 0 0 0 0 0, and it's going to take the highest priority, so here it's going to be 0 0 1. So you can see here that in the normal encoder, if I give like this, I'm going to get 0 0 0. In the priority encoder, if I give 1 1 and all zeros, I'm going to get 0 0 1. So it's a slightly different output characteristic between a normal encoder and a priority encoder. So what happened here is basically we have a don't care conditions. Okay, we have a don't care conditions, and it's just going to take the largest one. So you can see that for D6, the output is 6 regardless here if it's a 0 or 1. Okay, it doesn't matter. Okay, or D0 to D5, if it's 0 or 1, as long as you have a 1 on the D6, we are going to get a 6, whereas in the normal encoder we see that it is quite ambiguous, the characteristic there. Okay, so that's all for the lectures this week. So we have covered basically 4 main devices, medium scale integrated devices that we need to know. Okay, so as a summary, we have covered basically the multiplexer, okay, with various sizes, 2 to 1, 4 to 1, 8 to 1, different implementation. This is probably the most important, okay, in digital logic. One of the most important blocks is the multiplexer. We have also looked at the Demarks, which is less important, but also you need to know. We have looked at the decoder, okay, this is important. Okay, and then we have the encoder, which is not so widely used, but you still need to know. So 4 different, this is called the MSI, or the medium scale integrated circuit logic. Okay, and we have looked at 4 different 4 major blocks or components of the medium scale integrated circuits. Okay, so that's all for the lecture this week, and we'll continue the next part in the next lecture.